disturbance. So, I very pleasant good evening to all of you. Today is the second session of FDP 2023, and today lecture is and challenges in renewable study power system will be covered by Professor R.C.Bansal sir. The brief biography is Professor R.C.Bansal sir is has more than 25 years of diversified experience of a scholarship of teaching and learning accreditation, research, industrial and academic leadership in several countries. Currently, he is professor in the Department of Electrical and Computer Engineering at University of Sharjah. Previously, he was professor and group head power in EC department at the University of Patriots in South Africa. Prior to his appointment at UP, he was employed by the University of Queensland, Australia, University of the South Pacific, BITS Pilani, India, and Civil Construction will all radio. Professor Bansal has a many publication in IEEE transaction and he has also a, as an editor and reviewer of many reputed journal. Brief description is brief description of him. He will be covered the challenges of renewable energy in a power system. So I will hand over the session, Professor R.C.Bansal sir. All the topic will be covered by R.C.Bansal sir. Sir.
Yes, thank you, Dr. Navdeep, for kind introduction, and thank you, Dr. Navdeep and Professor Tiwari for kind invitation for this 2 weeks AICTE sponsored program regarding this energy challenge for the faculty development. In fact, it is a great opportunity and learning platform for these faculties, particularly young faculties, to have condensed knowledge in short period of time to interacting with the different faculties experts. So I will just share my presentation. Let me know, please, if these slides are visible.
Yes, sir.
Slides visible, please.
Yes, sir. Slides are visible.
Sir.
Yes, please. So again, please confirm that my voice clear and slides are visible so that I can start.
Yes, sir.
Yes,
both
sir.
Are, both are
okay.
clear.
Thank you all, faculty members, researchers. Good evening. So I will covering this topic, renewable energy integration, like in this current smart grid environment. What is the importance of this topic, and what we are going to basically cover the current trends for the electricity generation through renewable distributed generation. What are some of the requirements of this renewable distributed generation integration? What are the main challenge in these areas? And what are the main renewable distributed generation technology? There are several renewable distributed generation technology. However, the main and which are commonly used mostly worldwide are wind and photovoltaic system. So we'll briefly discuss about these two areas, and then of course briefly we talk about these microgrids, smart grids. I will share some of my experience around these areas as I have worked in the few countries. So Why we are looking for this renewable energy integration? We can see from this slide that as we are producing the electricity from this fossil fuel based power plants, coal, natural gas. So this electricity production causes the huge amount of uh, this fossil fuel plants cause the huge emission, and this is concern worldwide. You can see this big countries how much this pollutions is being caused because of this electricity generation. So that's why worldwide we are looking for the alternative, clean and sustainable ways of power generation. Because with this, we see that there are, um, with this pollution, there are, large number of issues, climate change, which we have not seen previously, this sudden change in this, weather conditions, and, so many issues what we are facing currently. So now worldwide we cannot afford to have electricity generation continuously using through this fossil fuel like coal based and natural gas. And of course these resources are limited one, and they are going to be exhausted very soon, the rate at which we are using for this electricity generation. So if we have a look the status that this fuel shares in the electricity generation. So here you can see that different notations, that this black one indicates this power generation through these coal-based power plants. So obviously the share of coal worldwide for use of electricity generation is on the decreasing trend, which is obvious because of this main issue of this pollution. And then, of course, you can see hydro and nuclear. So it is also a slight bit decreasing, because you see that mainly the large hydro, whichever are the locations, have already been harnessed. So as the load is increasing, demand is increasing. So net, there is this share. And then, of course, like, many countries do not like the nuclear gas based is constant, because this gas based power plant do not cause that much of pollution. Our main interest is towards these clean, sustainable, renewable power generation like wind photovoltaic systems. So you can see there is increasing trend, which obviously will continue. So if you see this current installed capacity worldwide, like say around end of 2022. So you'll see that this capacity is like say 12% or 13%. Of course, if we add the large hydro, then obviously it will be more. But still, we need to go big way to have this significant capacity addition through renewable power generation. So the researchers and faculty members who are working in this area about this renewable energy integration. So obviously this topic is not going to be outdated, at least for next minimum 20 years. So still there will be good interest in this area. Now let us talk briefly about these current trends for the electricity generation worldwide through renewable distributed generation. Now, as we had been generating electricity through this main coal-based power plants, large size power plant, um, using this big size generators. The main advantage was that economy to the scale was there. As we have the large generators, the cost of electricity production will reduce. That is the obvious reason. However, in the current trend for the renewable distributed generation, that economy to the scale for the large generators based on this coal-based or fossil fuel is no longer applicable. However, the current trend for the electricity generation is to have electricity generation through small scale power generation, smaller size of power plants situated close to the load centers. This type of renewable distributed generating plant have the several advantages. You can see main two advantages are significant reduction in the transmission and distribution losses. As we know that these renewable power plants located very close to the load center, the transmission line distance is almost zero. So the transmission and distribution losses are significantly reduced. And of course, this renewable distributed generation, being the green technology, offer the positive impact on the environment. And you can see that in the research work, as the researchers carry out the research, so they list the large number of benefit for the renewable energy integration. So there is one review paper you can see here in the listed here, integration of renewable distributed generation, a review published in IIT Renewable Power Generation. So very nice and very detailed review paper. So you can see in detail about this, different aspects of this renewable distributed generation. And then, my several PhD students have worked in this area, and some of these papers, like you can see that, with this distributed generation, how we can minimize the losses, and the study carried out around, location and sizing of the distributed generation plants. So when we are installing this distributed generation plant, so what should be the appropriate optimal location, optimal sizing? That is really very, very important. We cannot have just have this distributed generation located at any location of any sizing. Then we cannot get the expected benefits. So this location and sizing, we decide, after having this, proper research, proper simulation study carried out, and then we decide the optimal location and sizing. So even these distributed generation power plants, they can improve the quality of power supply, improvement of this voltage profile, and so on. So they can have several benefits. However, with the renewable energy integration, there are several technical challenges. Some of these are listed here. As we know that renewable distributed generation, like wind photovoltaics, they are fluctuating and intermittent in nature. Wind will fluctuate up to 25% in some short period of time. Then similarly, the issue for the photovoltaic, during night, no sunshine, even during the day, mowing clouds will come. So this renewable distributed generation are fluctuating and intermittent in nature, means that we need to have some kind of backup for the renewable distributed generation, particularly when we are operating in the isolated system. And when we are talking about these like traditional networks, they have not been designed for the DG integration, because these traditional networks, transmission lines, power plants, constructed maybe 50 years earlier, at that time, who had given the thought that, some point of time, people will have their own photovoltaic systems, or renewable energy plants will be integrated. So it means that uh, when we are integrating renewable power plants, so infrastructure may need to be developed to tap the renewable energy from, for example, wind power plants, offshore wind farms. So this infrastructure needs to be developed. And another important aspect, we know that when we are integrating distributed generation to the grid, the power flow becomes bidirectional. So bidirectional, we know that, uh, consumer is drawing power from the grid, but at the same time, customer have their own photovoltaic systems. So excess power from the PV systems can be fed back into the grid. So it means that power flow becomes bidirectional. Then another major challenge what we see with this power flow became bidirectional. The major issue what we face is the protection system for this system. So we need to have the significant modification in this protection system. The existing protection system may not work well, because in the traditional power system we use the single directional relay, which were less expensive. However, as the power flow becomes bidirectional, so single directional relay will not work well. So in that situation, obviously we need to modify the protection scheme to protect our power system. When we are integrating distributed generation to the grid, so there are several interconnection requirements covered in IEEE standard 1547. So these interconnection requirements include fault ride-through capability, voltage and frequency operating limits, active power control in terms of set point, ramp rate, uh, reserve requirement, frequency regulation, reactive power control, voltage control, other requirements in terms of power quality, protection, etc. So this topic itself is so detailed that it can need the separate session to discuss in detail. So I will briefly explain some aspects of this distributed generation interconnection requirement. As you can see that first thing, like fault ride-through capability. If the fault occurs on this power system networks, which is integrated through renewable power plants, so what should be the approach? In the past, when the fault occurs, then these renewable power plants will be uh, uh, disconnected from the power system network, because the main aspect was to protect the renewable power plant itself. However, now the technology has progressed much, and now we do not immediately disconnect the renewable power plants, but these renewable power plants stay connected. Not only connected, but they try to help in recovering the fault conditions, because the technology has improved and they can try to help in recovering the fault. For example, now we have the photovoltaic systems. Previously, we were operating only at the unity power factor, but now we can operate the photovoltaic systems at leading or lagging power factor. It means that these PV systems, through these converters, they can supply the reactive power. Reactive power supply means that they can help in controlling the voltage. So this way, uh, renewable power plants will not be immediately disconnected, but they will stay on the grid and they help in recovering of the uh, fault currents, fault condition. Talking about the second very important aspect, voltage and frequency operating limits. So we know that we have to operate our power system network uh, in that voltage and frequency should stay within the limits. When we have our system's nominal frequency 50 hertz, you can see these two graphs. Upper one is the case for the Denmark and below one is for the China. So we would like to operate our power plant within the frequency, nominal frequency in the upper graph, you can say between 49 to 51 hertz. If the abnormal operation is there, in that case, within the specified period of time, we have to bring the system back to the normal operation. If it takes more time to bring the system to the normal operation, it means our control system is sluggish and that can make this power system unstable. So within the within the allocated period of time, we have to bring the system back to the normal operation. And then of course we have voltage operating limits. That voltage should not deviate plus minus 10%. Voltage should stay within the limits. And in the below graph, you can see that this normal operation in case of the China has been narrowed down. Of course, there are international standards like IEEE 1547. This is mainly applicable for the small size power plants, not applicable for the bigger size of power plants. Then the countries can design their own standards interconnection requirements, because generally many people think that when this renewable energy integration is there in the grid, that will affect the quality of power. Okay, but that may not be completely true. So how you design and implement these grid codes? If you tighten the grid code requirements, you have this narrow operation for the normal operation. In that case, if there are poor quality independent power producers, so they will not successful in getting the bid requirements for integration of renewable energy. So they will not be able to successful. Only the quality independent power producers will get success in getting the bids to supply the renewable energy. So this way, like how we design and implement these grid codes through which we can really maintain the quality, and our quality of power system will not be affected. Then you can see that there are requirements in terms of active power control, reactive power control. Active power, you'll see different aspects like the set point, ramp rate, reserve, frequency regulation, etc. So keep in mind that we are operating renewable power plants along with uh, fossil fuel-based power plant. So we have to keep separate aspects in mind, that different plants have the different ramp rate, okay, at which speed they can take the load. For example, we have car. So what is its ramp rate? how fast it can pick up the speed. Same way, like power plants, like we have based on the coal based, based on the gas based. So different types of power plant have these ramp rate, at which rate within the what short period of time they can pick up the load. So in the current deregulated environment, this ramp rate, etc., this becomes very important. Now, like say, what is the meaning of this reserve? Uh, if this next day electricity we have to produce. So how much load will be there? It will also depend upon this, how we are going to have this weather for tomorrow. Uh, this load will depend some extent on that. But renewable energy production will significantly depend upon this weather condition, how will be this wind velocity, how much will be the sunshine. But the consumer needs the electricity irrespective of what kind of weather we have. So in that situation, these utilities, for example, uh, based on this coal-based and gas-based, like our utility NTPC, for example. So they have to generate the electricity to meet the consumer requirements. So they have to keep their plant in the hot conditions, means that they have to use their uh, fuel to keep their plant in the hot conditions. So there is like a lot of issues, uncertainty, reserve. So all these aspects we have to keep in mind. Keep in mind. So these different topics really very interesting because of the time constraint. I cannot go into much detail, but we are happy to have more discussion during the interaction time. Then let us talk briefly about this main renewable distributed generation technology. First, we'll talk about the uh, wind, both wind onshore and offshore. So power generation through onshore is quite mature technology, and this power generation through offshore is relatively new technology. So the cumulative worldwide installed capacity from the onshore, you can see left side, by end of 2020, installed capacity was around 700 gigawatt. Okay. Then in the year 2021, around 72 gigawatt was added. So how much was added in 1 year? So you can see roughly it is around 10% of this cumulative installed capacity of the previous year. So what you can see that growth rate every year from this onshore wind is around 10%. You can also see from this slide that which are the countries who are the leader in the power generation from the wind. So obviously you can see that China, which is contributing around 40%, then US around 17%, then followed by Germany around 8, India around 5.5, then other countries like Spain, France, Brazil, etc. So, but you can see large number of countries are, generating electricity through these wind power plants. Let us see the status for the installed capacity from the offshore power plants, wind power plant installed inside the sea. So this is comparatively very new technology. By end of 2020, installed capacity was around 35 gigawatt. However, in the year 2021, 21 gigawatt gigawatt was added. So you can see in 1 year, significant capacity was added. So until up to 2020, offshore was mainly installed in the northern Europe. However, China also started taking great interest in the power generation from the offshore, and you can see that uh, out of 21, significant capacity around 19, significant capacity was contributed from the China. So you can see in 2021 worldwide, out of 45, like out of 53 new offshore wind farms, 45 were in China. So mostly you can see that in 2021, most of the contribution was from the China. So now China has started taking great interest and significant capacity addition in the offshore power plant. So in this slide, you can also see the global cumulative wind power installed capacity. If we see the situation around 2020 or 2022, if you add, wind onshore, offshore, so current installed capacity, we have around 1000 gigawatt. We add both onshore and offshore. Now, how much we can expect, maybe say by 2050? So these different models have been proposed by the researchers. So you can see what we may expect by 2050. So if you see from here, maybe something say around 4000 or 5000 gigawatt. Currently, we are having around 1000 gigawatt. So if we say we can expect say 5000 gigawatt, means that by 2050, we can have 5 times of the capacity we may achieve what we have currently today. Now let us briefly discuss little bit technical aspects of these wind power plants. So as we know that we have two types of power plant from the winds. One is what we call as the horizontal axis wind turbine, which is commonly used in this power generation for all these commercial power plants. So this picture you can see is the horizontal axis wind turbine, what we call as the HAWT. So here you can see the axis of the shaft is basically parallel to the ground. So this is horizontal axis wind turbine. Here, the gearbox generator. So these are installed, placed in this nacelle, which is at the significant height from the ground. And here you can see this wind turbine, and you can see some of these parts, what we see here. These wind turbine blades, then we have these several controls mechanism associated with the wind turbine called as the pitch control, or here this motor you can say yaw control. So some of the controls associated with that, this shaft of this wind turbine, then gearbox. So generally this gearbox is required to match these two different speeds. As we know that speed of the wind turbine is relatively very slow, whereas the speed of electrical generator is very significantly high. So how we interconnect these two devices, it is through the gearbox. Now, some of the technical aspects, as one of the very important technical aspect we use called as this tip speed ratio, TSR. Okay. So we have the different types of wind turbines. As I mentioned, this slide, horizontal axis wind turbine. The another we can have what we call as the vertical axis wind turbine. So vertical axis wind turbine, for example, this there is rotor. So these vertical axis wind turbines are not commonly used. Same is the case for this multi-blade wind turbine. So we are not using the multi-blades wind turbine. We are mostly using the two blades or three blades wind turbine, which you can see here. Uh, this is the two-speed blade wind turbine. This is the three-speed wind turbine blades. So all the commercial wind turbines will be either two blades or three blades wind turbine. Okay. As we know that what we can have the maximum efficiency from the wind turbine, the theoretical limit, what we call is the base limit, which is 59.3%. So that's the maximum efficiency what we can achieve. Limit, or this is the curve what we see the ideal efficiency. However, what we can practically achieve from these modern three blades or two blades wind turbine, which can be, if you see three blades, it can be something from 40% to say this 42%. With two blades, you can see it can be from 40% and it can go to say 47%. So you will see that this variation from 40 to 47%, this is quite significant variation. On which factor it will depend. So obviously you can see this will depend upon this, the term what we call as the tip speed ratio. So tip speed ratio, basically you can see if we have these three blades, so which is here around 3 to say 5.5, whereas in case of two blades, this is something 4 to 7. Okay. So this I am referring from this textbook, very popular textbook, GM Masters, Renewable and Efficient Power Plants. Okay. So here this tip speed ratio, very important term. What is that? That what is the speed at the tip of the blades? We have this natural speed of the wind turbine, whatever speed we are getting from the nature, we do not have any control over that. But what type of wind turbine we have, and with the speed, how much will be the speed at the wind tip? So that the term what we call as the tip speed ratio. So which will decide whether we are able to extract the maximum energy from the wind turbine or not. So you can see that this term very much similar to what we use in the photovoltaic system. We call it MPPT. So similar term you can see here related to tip speed ratio. Here also objective is to use through this variable wind speed. Wind speed is variable. To this variable wind speed, how much maximum energy we can extract from the wind turbine. So what should be the tip speed ratio so that we can extract the maximum energy from the wind turbine. Now let us talk about the different wind turbine technology. I will go in very brief. So this you can find in several research papers as well. So as per IEEE, we have these different types of generator technology. We call it type 1, type 2, type 3, type 4, or in Europe, they are also called as the type A, B, C, and D respectively. So we'll briefly talk about this slightly with the figures so that you can have slight bit good understanding. So you can see type 1, type 2. So you'll see very much exactly same, except you see in type 2 is basically in the type 2 rotor circuit, we can add the external resistance. So both you can say are based on the induction generator. The first one, type 1, is the squirrel cage induction generator, whereas type 2 is the slip ring induction generator. In type 2, we can add the external resistance in the rotor circuit, thereby varying the torque and slip characteristics we know very well. So type 1 almost fixed speed. Uh, there is limited control of slip, just like say 2% to 3%. So we cannot have much control on the real reactive power. With this adding of this resistance in the rotor circuit, we have more control on the slip up to 10%. It means we can control more reactive power. Control of reactive power means that we can control the variation in the voltage, particularly during the fault conditions. Now, talking about the type 3 and type 4. Type 3 again based on the induction generator. However, what we call this type 3 very popular as the doubly-fed induction generator. So in case of doubly-fed induction generator, power can be fed into the grid both from the stator as well as from the rotor circuit. However, we know that frequency in the rotor circuit is not the same 50 Hertz frequency, but when you have to feed power into the grid, so we have to bring this frequency from the rotor circuit back to 50 Hertz before that power is being fed into the rotor circuit. So we require these converters, power electronic converters, and this rating of these power electronic converters is around 30% of the rating of this machine. For example, if we have this wind turbine generator, its rating is, for example, 2 megawatt. Then 30% of 2 megawatt will be around 660 kilowatt. So we need this power converter rating around 660 kVAR. Talking about the type 4, which can be based on this induction generator or synchronous generator. Synchronous generator is more popular. So here basically it is again uses this power electronic converters. And here, of course, we are just only drawing the power from the stator terminals. So this converter rating is same as that of these generator ratings, like converter ratings have 100%. However, with this design, this control of frequency, control of this reactive power or control of this slip is up to 100%. So there is significant flexibility. Of course, the cost of this generator increases, but we are able to extract more power from this wind turbine. So you will see that out of these 4 types, type 3 and type 4 are very common or commonly used for the electricity generation. Type 1 and type 2, they are what we can say are comparatively old technology, and they might be used, in very small size of this wind turbines, maybe isolated, very small size of wind turbine. So just to give you some practical examples of these different types of wind turbine system. So here you can see an example of Vestas V80 1.8 megawatt wind turbine. So it is Vestas V80 means this wind turbine diameter is 80 meters, and this individual wind turbine power rating is 1.8 megawatt. So this is an example of variable slip. So it is type 2 generator, in which by adding the resistance in the rotor circuit, optimum slip can be achieved and optimal operation can be there. So this wind turbine generally operates between this speed of 9 to 19 RPM. Then we can have this other popular type of generators. One example you can see from the WFED induction generator type 3, very popular. So here you can see that with WFED induction generator, from the stator terminal, power is fed directly to the grid. And from the rotor terminal, power is fed to the grid through these converters. So we have converters through which power is fed into the grid. So this is example of like General Electric 1.5 and 3.6 megawatt DFIG based generators. So this G, like in the year 2011 in US, these were the best selling wind turbine. But now, of course, the size of wind turbine is increasing. So might be, 3.6 megawatt. Now talking about the another generator technology, type 4. So here type 4, again with the General Electric 2.5 megawatt wind turbine based on the type 4 permanent magnet synchronous generator. So here power is drawn only from the stator terminal. The generator technology is PMSG. So here we have the converter rating, same as that of generator rating. So here converter rating will be 2.5 MVAR. So this again, PMSG getting very popular generator technology. So mainly in all the wind turbine power plants, mostly we have type 3 or type 4 generator technology. Now you can see this very interesting point. This wind turbine classification, as we call as the fixed speed wind turbine, or what we call as the variable wind speed turbine, what we call as the old wind turbine technology or new wind turbine technology. So here on the left side, it is an example of squirrel cage induction generator. In fact, squirrel cage induction generator, it is Vestas V82-1.65 means the wind turbine rotor diameter is 82, and this individual generator is able to generate 1.65 megawatt, but it is squirrel cage induction generator technology, means that it is type 1 type of generator. In this another case, you will see that it is General Electric 2.15 megawatt with wind turbine blade diameter of 103, and it is PMSG, Permanent Magnet Synchronous Generator. So it is type 4 generator technology. So here you will see that we are seeing these two graphs. One is for this power. So power, this curve, what we call as this 3-speed, cut-in speed, rated speed, and furling speed. And this is the power curve. But if you see this another curve, what we call as the coefficient of performance, CP. So on this left side, you will see that this coefficient of performance, how significantly this is varying when this wind speed is varying, for example, between say 5 to say 10 meter per second. So you see that if this wind speed was 5, you see that CP was 0.2. But when it becomes, for example, wind speed 7.5, the CP will go to peak, that is around 0.5. However, again, if this wind speed is decreasing, then the CP will again significantly go down. As we know that we have this power available in the wind, which is given by half rho A V cube. How much we can extract from the wind turbine? It will be given by half rho A V cube multiplied by CP. So if we have high CP, it means we are able to extract more power. So here you can see CP is significantly varying with the wind speed. Even if the wind speed is very high, but the CP is even lesser than 0.2. So power extracted is really very less. Even if this wind speed is very low, power extracted is very low. Only when we have this wind speed, just like only around say around 7.5, then the CP value will be high and it will be able to extract this good power. However, the wind, what we are getting, we don't have much control. We don't have control. You can see other case. For example, here this CP, this curve is quite flat. Even if this wind, which was like for example 5 meter per second, or it varies from 5 to 10, you can see this CP, which is almost constant. Even with the variation of wind speed from 5 to 10, what maximum variation we see in the CP is it can be 0.4 or it can be 0.42. So the CP is almost constant in good range of variation of the wind. It means with this modern wind turbine technology, which are variable wind speed turbine, we can extract good amount of electricity. Now, as we know that how this progress in the wind turbine technology has taken place, how this individual wind turbine have grown into this size, their wind turbine diameter has increased, individual wind turbine power production capacity has increased. You can see some of the example, like say Mitsubishi 1 megawatt wind turbine with the 62 meter wind turbine blade diameter, Siemens 82 meter diameter wind turbine, power capacity 2.3 megawatt. Then you can see last one like this 164 meter wind turbine diameter with the 7 megawatt individual wind turbine. So you'll see that this 7 megawatt individual wind turbine requires the wind turbine blade diameter of 164 meter. If you see that one football ground, which is 110 meter. So this blade diameter for this 7 megawatt wind turbine, it is, you can see, almost 1.5 times of the football ground length. So you can see how big are the wind turbine diameter. Now this equation very popular, what we are using in this wind turbine power plants, very commonly used equation. Power available in the wind given by rho A V cube by 2. So where V is the wind velocity, we would like to have this our wind farms in the good windy area to have this more power produced from the wind turbine. Then area, as you know, area is pi by 4d square. So power produced will vary square of the diameter. As we increase the diameter, the cost will also increase, maybe in the same proportionate. However, power produced will increase square of that, square of the diameter. So as we have this bigger size of wind turbine, of course, to construct, it will add more cost. However, cost increase in the same proportionate of the diameter, but power produced will increase square of the diameter. So there is great economy associated with the large size wind turbine. Therefore, this motivates to go for the larger and larger size of the wind turbine. So same is also explained here how this wind turbine generator rating has increased. And this increase in the rotor diameter, what is the role of power electronics, what is the generator technology. So this you can see, you will find in this paper published in electric power components and system, and some other papers we can also see that mainly we started this wind turbine generator technology for generating electricity around 1980s. We used to have wind turbine ratings around 50 kilowatt with the wind turbine diameter around 15 meter. Generator technology was mainly squirrel cage induction generator. Then up to 2000, we are having either this squirrel cage or slip ring induction generator. The wind turbine rating increased up to 1 megawatt. However, in year 2000, there was breakthrough in the generator technology. We got very popular generator technology, DFIG, so which uses around 30% power rating as the converter rating. The rotor diameter is around 80 meters. Thereafter, we are using both DFIG and then, of course, new technology, what we commonly call as the permanent magnet synchronous generator technology. So then there is continuously increase in the wind turbine rating and its associated diameter. So you can see by 2018 we had 190 meter wind turbine with 10 megawatt power. And very recently you can see that Siemens has unveiled 14 megawatt of the wind turbine used in the offshore wind farm with the wind turbine rotor diameter of 222 meters. Even this wind turbine can be increased power up to 15 megawatt. So one wind turbine can produce electricity up to supply power to 18,000 house in the Europe. And if we have like 30 turbines, so they can supply power to, a city in Spain. And the Siemens is the leader in this power generation from the wind, both onshore and offshore. It has already installed over 100 gigawatt of this power. So you can see its share. If we say that total worldwide 1000 gigawatt, so its share more than 10%. And by installing this wind turbine, obviously it has significantly reduced the issue of this CO2 emission. Okay. So let me know if you have to take the break or I can continue. Please advise.
Hello.
Yes, please.
Yes, sir. I will ask the participants.
Yes, please.
A break can be taken, sir. At least 5
Okay,
minutes.
so
10
we will
minutes.
take the short break, maybe 5-10 minutes, and then we will start again. Eh?
Okay, sir. After 10 minutes, sir.
Yes, yes. After 10 minutes, I will join
just,
again.
Just after 10 minutes, sir. Okay.
Yes, I will just join after 10 minutes.
All participants can resume after 10 minutes, or they can take a break for as per your requirement.
Melbourne, Sydney, Brisbane, and many other countries worldwide, many main cities are just, close to the offshore. Means that you'll find load very close to the generation, offshore wind generation. So the development cost will obviously reduce, transmission length will reduce. So this is one great plus point. Then, of course, you will see that the cost of this construction of foundation, etc. is there. So construction cost is more. However, we know that wind velocity is higher at the offshore, and thereby we are able to use this large size wind turbine. Whatever you are seeing, this big size of wind turbine like 10 megawatt, 15 megawatt, obviously this large size of wind turbine are obviously using the offshore. So offshore wind turbine are able to produce more power because of higher wind velocity. So the cost issue can somehow be neutralized. So as there is more and more capacity addition worldwide, obviously the cost from the offshore wind turbine will go down, and then this technology will be more popular and will be common use. Now, just to briefly talk about, one very small size wind turbine. So this you can see an example of this vertical axis wind turbine. Here, shaft of this wind turbine is vertical to the ground. There can be several designs. So this is one of the design for the vertical axis wind turbine. Small size wind turbine, 3 kilowatt rating, which can be installed on the rooftop. So this placed at the Victoria University in Australia. In fact, I examined this researcher's PhD thesis. So this researcher explored the possibility of using the small size wind turbine on the rooftops. Student conducting the research in the Victoria City, Australia, and then Tamil Nadu state in India. What is the possibility? So if in future this technology is mature, successful, then we in future we may also see that, where there is good wind velocity, we can use the small size wind turbine on the rooftops of the building as well, along with the photovoltaic systems. So this might be another technology. Now, let us talk about the another very popular technology, electricity generation from the solar photovoltaic systems. So we see that we receive the huge amount of power from the sun in sun equivalent of like 1.2 into 10 raised to power 8 gigawatt. And if we can tap this power just for 1 hour, so it could satisfy the entire demand for the world for 1 year. It means that we have huge potential of electricity generation through sun. And this PV technology is very convenient, offers large number of advantages. There is direct conversion of solar light into electricity. This is very much environment friendly, reliable, involves no moving part, complete silent operation, low operation and maintenance costs, and can be installed very quickly. If we compare with respect of other power plants, for example, we have power plant from this large hydro or power from coal-based power plant. So gestation period could be around 5 to 8 years. However, if we have the large size photovoltaic power plant, it can be constructed and made operational within the period of 1 year. So this power production from photovoltaic systems is very quick. So that way, these photovoltaic systems offer large number of benefits. And so you can see that this technology got very popular in very short period of time. Of course, it has some issue. One issue that it used to be very costly. This was one of the major barrier that this technology was not so popular because of this significant cost. However, now the cost issue is gone. If you see the situation year around 2012-13, the cost of electricity produced from the solar, it used to be around 20 rupees per unit of electricity. But if you see the situation now, so electricity from the solar, it has come down of the order of 2 rupees or 3 rupees per unit of electricity. So within the short period of 6 years, the cost has significantly come down. So now it is, very much affordable cost. Whatever electricity we are getting from the other sources, this power from this solar is also in the similar range. Now, these photovoltaic systems, we can have the different configurations. These power plants from the photovoltaic systems, you can see can be very small size installed on these individual houses, or it can be medium size installed on this like these commercial buildings, university buildings, etc. Or these can be large size power plants installed on the grounds. So there is lot of diversity when we are talking about the photovoltaic power plants. As we know, these photovoltaic power plants will generate the DC supply. Then our most of the load currently is the AC. So obviously we need these power converters to change from DC to AC. And as the backup, we have this power from the utility where there is the grid supply. So in this case, we can use power from this solar, but when we do not have power from the solar or less power, we can take the power from the grid. If you excess power from the solar, we can feed power back into the grid as well. That is basically called as the concept of the net metering. This PV can have configurations as you show, can be connected with the grid, or it can have standalone. So when we are talking about the standalone, then how we are designing, the important issue is about the backup. So backup it will obviously have the battery storage system. Additionally, it can have the diesel generator as well. So we have this another configuration, what we call as the standalone system. Then we can have another standalone system. However, its application is totally different. These photovoltaic systems can be used for the irrigation purpose, like our country, which is agriculture based. So this PV can find the great applications for irrigation, water pumping purpose for the farmers. So we want to design our systems really very low cost. So we obviously will avoid the batteries, no need for batteries. We have PV plants, then simply DC motor, and which will use to supply the power, supply to the water to the farmers for irrigation purpose. Here, we whenever we have sunshine, DC motor will run and it will supply the water. So doesn't it matter whether we have, in between no sunshine, so it doesn't cause main issue, because irrigation, it's not very specific time related that it should continuously be there or not. So there is no major concern. So we don't need any backup like this batteries to unnecessarily increase the cost. So this is like another very important application. Then I will briefly touch upon some of the technical characteristics. I will not go into the detail, but you see that we have this photovoltaic system. We are connecting the load, and then you see we have basically IV characteristics for these PV systems. Then we have this load. Load will have its own IV characteristics where these two curves cut each other. That will be operating points. Obviously, we will like to operate our PV systems close to this knee point to extract the maximum power, what we call as this MPP point. However, we can adjust the load manually, resistive load. However, it is not possible to keep on doing manually. Even we adjust it, but you'll see that the sunshine keeps on changing throughout the day. So even we adjust this manually corresponding to MPP condition, but still as the sunshine keeps on changing, so it will not stay corresponding to MPP condition. You can see here in this slide, for example, if we adjusted this IV characteristic corresponding to one MPP condition, but as the sunshine keeps on changing throughout the day, so operating point, MPP operating point will not be this, but the operating MPP point will be this. So basically, we need to have, some automatic device, which can automatically, take care for this sun position and accordingly operate our system corresponding to MPP condition. We have this, for example, DC motor in case of this water pumping application in the irrigation purpose. So we are aware of this DC motor operating characteristics. In the starting, it needs the high current, but once the motor can be started, then it can be operated with the keep on operating with the low current or the lower voltage. So here concept is that in case of DC motor water pumping application, if we can use a device called as this linear current booster, which will operate like the MPPT. So when we have this linear current booster, which will help in starting the motor, actually if we do not have this linear current booster, in that case, the motor will start when we have the sun insolation corresponding to say 400 watt per meter square. Maybe that insolation we may get, say, for example, 10 or 11 a.m. in the morning. However, if we use this LCB, so in that case, basically the motor can be start, for example, corresponding to 200 watt per meter square of the sun insolation, which may achieve say 8 a.m. in the morning. So what I'm trying to say here that with this device like LCB, the operation of this motor can be extended hour in the morning or same way in the afternoon. So basically this motor can keep on operating, running for the longer duration. So this power output, or what we call this efficiency, so it can be enhanced. So this can act like this MPP. Then of course we have this battery as the backup as well. So we need to understand a little bit about the battery characteristic as well. I will not go into the detail. So this slide you see is what we call the ideal battery characteristics, which is kind of like this straight line. But practically we have this battery characteristic which is slightly tilted on this like left side or right side, depending upon whether this battery is in the charging mode or in the discharging mode. This MPPT or MPP tracker, this is very important, one of the research areas. So a lot of research being done around this area. So just to briefly explain what is this MPPT. Again, I gave you the example. So here we have this PV systems and load, and then we have basically kind of MPPT, which can be basically backend boost converter. So basically what we have this voltage from this solar and how much voltage we need corresponding the load to have this MPP condition. So this circuit comprising of like your switch, which is not this ordinary switch, but it is based on the IGBT power electronic switch. Then of course we have this inductor capacitors connected through this diode. So you are sorry, transistor switch comprising of IGBT or FET. So it flip-flops in the frequency around 20 kilohertz. And basically what we are doing here, we can change the duty cycle. By changing the duty cycle, mainly you can change this output across the load. And by doing that, you can get the MPP condition. I'm not going into the detail, but you can see basically this equation here, ratio of output voltage and input voltage. Simply, it is related with the duty cycle. So duty cycle, you know that how much duration in one cycle we keep the switch on and off condition. So duty cycle can be adjusted to say, for example, 0.5, or it can be less than 0.5, means that the switch is on lesser than 0.5, or switch can be on greater than 0.5. Accordingly, by changing this duty cycle, the voltage output can be changed, and it can lead to have the NPP condition. Then another very important concept, what we talk about the DC and AC rated power. As you know that the photovoltaic panel will produce the DC power, and we want to estimate related to our load, which is AC. Then to make an estimate. Basically, our grid connected system will of course comprise of the modules and power conditioning unit, including inverter to convert DC into AC. Then of course, like we want to have this standard performance under standard test condition. We can compare the performance of the different PV panels. So STC conditions is like one sun, insolation, air mass ratio of 1.5, shell temperature of 25 degree. But when this PV system is actually put into the field, the actual power delivered will be how much that we call as this AC power. So this AC power will be obviously AC power will be DC power from this PV panel under standard test condition multiplied by the conversion efficiency. So this conversion efficiency, it is not only the efficiency of inverters, but it is overall conversion efficiency comprising of whether the PV panels are clean or dirty, if there is any mismatching in the modules, or if there is difference in the ambient conditions. So if you consider all these factors, so this conversion efficiency, the power losses can be of the order of 20 to 40%. Now, other factors you might be already aware, but this mismatching of the module can be slightly new to some of these researchers. So here, what is this mismatching? Like if we have PV panels from the different manufacturers, its power rating can be same. Say for example, 180 watt, but this 180 watt can also be there that, for example, it can be 30 volts and 6 amps, or it can also be 36 volt and 5 amps. So both will, if you multiply, it will lead to have 180 watts. However, if these two PV modules, both power rating 180 watt, connect them in parallel, so we'll think that power output you will get 180 plus 180, 360. But if you practically connect them, you can end up getting, instead of 360, you may end up getting a 330 watt. So this is what we call as the mismatching of the module. When you are having this PV module, like one you already have, then you know when you want to start the additional one, then you think that okay, power rating is same. So it is not only to match the power rating, but there has to be matching for this voltage and current rating of the module as well. Otherwise, because of this mismatching, there can be some power loss. Now, when we want to have this, design of the PV systems could be grid connected or could be isolated. So how you are designing this grid connected system? If you are talking about the design of the grid connected PV systems, so that design is comparatively easy. It is, basically starts around some of the non-technical parameters. Non-technical parameters, like you will be interested in knowing that if you want to have our own photovoltaic systems and we want to, supply power to the utilities, then obviously we will be interested that how much is our agreement that utility will be willing to buy and to provide that much of this units of electricity per year. What size of this PV module will be required? How many PV panels will be required? And for that much of PV panels, how much space will be required? So first we have to see how much space we have available for these PV systems. So only we can install that. And then we have to also see that how much we want to invest. So mainly this design is mostly around the non-technical parameters. However, some technical parameters, basically you see that what are the different sizing of PV panels, converters, etc. are available. We give consideration, but mainly you'll see that the design is around the mostly non-technical parameters. However, when we are designing the standalone photovoltaic system, so in that case, the design is around technical, more around the technical parameters. So when we do not have any backup, we are talking about the standalone PV systems, then backup is really very important. So what kind of backup we have? It is batteries, or it is backup diesel generator as well. So the backup is really very important. And then for the load, how much load we want to keep the backup. If you want to have backup for whole load, then obviously the cost of the system will be significantly higher. And whatever the different types of loads we have, either we are designing the household systems, designing the office, so different types of load, what we will expect it to have potentially. We have to make the estimate of the load. We calculate the load. Accordingly, we will design the photovoltaic systems. Accordingly, we will have design for our backup systems based on the batteries, or even based on what we call as the diesel generator. Now, when we are designing these standalone PV systems, so here design will start with an estimate of the load that needs to be supplied through this PV system. And then some other points like this about the backup, battery storage systems, etc. And then the load, what type of load we have, all load AC, or we can have partially DC load. If we can have partially DC load, that will avoid unnecessarily using, all inverters, because as we are inverting, efficiency loss is there. Okay. Then what fraction of the full load we have the backup generator, because if you have 100% backup, it means generator size will increase, and that will add to the cost as well. And then we have to also see what kind of load we have. Either we have all static load, or we have dynamic load as well, like motor load. And for motor load, you have to also keep in the in-rest current condition as well. Okay. So I'm trying to, just quickly cover as much as I can. Then some statistics, like how this development in the photovoltaic capacity has taken place worldwide. You can see this PV system started quite late. Wind started around 1980s, but this PV started 25 years later, around 2005. But how this growth has taken place, mainly started say around, even still you count 2005, still this in the period of around 17 years, how this capacity grown has taken place. You can see this installed capacity. Now this may not be exactly same, as I took it from this Wikipedia, because it is still an black one is still an estimate, but we can see that by end of 2022, we already have this capacity more than 100 gigawatts, okay, more than the wind. The another point I want to mention that how much is this cumulative growth. So you'll see that this growth varying between 32% to say 23%, say average around 25%. So every year growth is around 25%. What does it mean? That within the period of 4 years, worldwide installed capacity from photovoltaic, it will just double. Whereas in case of wind, the growth rate is around 10%. What does it mean? That it will take 10 years to double the capacity from the wind system. So you can see that growth rate installed capacity from the photovoltaic is growing very, very fast. These are, you can see some of the country leader in the power generation from the photovoltaic: China, US, India, Japan, etc. Now, very important point I want to touch upon that, PV systems, as I mentioned, it can be small size, medium size, but particularly more important now this PV plants we are seeing like these big power plants, like this conventional power plant, even more than the capacity of 2000 megawatt capacity. So when we have this power plant more than 2000 megawatt capacity, we call this super thermal power plant. So we in India, we have at least two power plant more than 2000 megawatt capacity, one in the Rajasthan state, another one in the Karnataka state. So and we have, of course, few more during the construction stage. More important that our utility NTPC plans to have significant investment in the renewable. They want to diversify their energy mix. Currently 96% to 70% means that 70% from the coal and gas, 30% from the renewables. Then other countries like China, Egypt, UAE, Mexico, USA, they have also large size these PV plants. Talking briefly about this, the University of Queensland case, I worked previously at the University of Queensland in Australia. So around here you can see that in 2011 or 12, University of Queensland initially installed 1.2 megawatt photovoltaic system. Then it was increased up to 5 megawatt on the rooftops of the different campus buildings. So in real time, you can see what is the trend for power generation throughout the day, how much electricity it has produced since its installation, how much savings it has made. You can find a lot of interesting information if you visit through this website. So you can find several interesting research papers based on this practical experience, what type of PV technology, inverters, batteries, etc. have been used to get nice understanding about the practical aspects. Then when we are talking about these PV integration issues, as I explained, that PV system can be small, medium size, very large, like the large size power plant. So these technical integration issues are really widely varying. When we are talking about the small size PV system, we talk about the issues like this moving clouds, etc. Or if you are having this large number of small size power plants installed in the localized area, we talk about the issues like this power quality, voltage regulation, etc. However, when we are talking about the large size power plants, I explained previously. So then we talk about this issue, how the overall stability will be affected. Okay, then there comes the question that when we have these PV systems connected to the grid, whether we should have battery storage system. If we have battery storage system, which way it can help. So here in this graph, you can see if we have this battery storage system, it can help in meeting the peak demand for the utility. Then touching upon this very recent development at the University of Queensland, Australia. So they have 64 megawatt of solar power plant. So to make this 64 megawatt of solar power plant requires 200,000 panels, and this is great facility, can be used for, of course, powering the households in the Queensland state, and then of course this can also be used as the teaching and research facility as well. Just to briefly touch upon the situation of our country, how much we have installed capacity, around 400 gigawatt. So out of this 400 gigawatt, currently we have non-renewables around 60%, renewables around 40%, non-renewables mainly coal still more than 50%. Then renewables, we have large hydro. We are including large hydro as well in the renewable, wind, solar, bio, small hydro. So this making around 40%. So still we need to go big way to have, green power generation, reduce the share of the coal. We show in the previous slide that NTPC taking the great efforts. NTPC mainly company based on this coal and gas. When I was at BITS Pilani, I covered almost all their plants, visit all the plants. We used to have this BS Power Engineering program. So mainly coal and gas based power plant, but now recently they have diversified their business in the renewables, and yeah, they hopefully that we will have more green power. Now I know time is running out, but I will try to complete around 15 minutes. Then we'll have around 15 minutes for the discussion. Talking about this microgrid hybrid power systems, which can be like in this grid connected or in the remote, hybrid, isolated. So here we still have these communities, remote areas which do not have power coming from the grid. So how they made the electricity requirement, mainly small size diesel generator, and power produced from the diesel generator is really very costly because of the cost of fuel, operation and maintenance cost, transportation cost. However, if along with diesel, other natural resources available in those areas could be wind, sunshine, bio, small hydro, if they can integrate it along with the diesel. So this is what we call as the hybrid power system. Cost of power plants can be brought down. The capacity of these plant can be increased. Community can be supplied for more number of power. So this can be a nice way of supplying power to the community. So this slide gives you a comparison. This paper published in 2015 in Electric Power Components and Systems, talking about the status of different renewable energy technology. Some of the technology we covered, like wind onshore, wind offshore, photovoltaic systems. These are, you can say, main technology. Then there are some other technology, what we call as the concentrating solar power, wave, fuel cells. So these have not been so popular might be in the experimental stage or so. But some technology we can see are getting very popular, like battery storage technology used in the renewables, also used in the electric vehicles, hydrogen also coming up. So it gives you present status. We already covered present status. Some of the challenge we covered talking, for example, wind onshore. There are some research challenge opportunities around, converters based on the new semiconductor devices, medium voltage based converters. Then talking about the offshore, some of the challenges are, offshore foundation, interconnection of onshore and offshore wind farms, harmonics and stability issues, high maintenance issue. This cost of the offshore will come down as we have more and more capacity addition. Then talking about the photovoltaic system, some of the issues that how we improve the efficiency of PV systems, better material in film PV, for example. Design of these micro inverters. So there are several challenges and opportunities. Then briefly touching upon the topic smart grid. So smart grid is not a replacement of the existing grid, but complement to it with the features like we need to have central and renewable distributed generation, integration of more and more renewables. Electric vehicles will likely to come. Energy storage is very important. Phasor measurement units to maintain the health of the transmission lines. A smart meter definitely needed in the mainly in the distribution systems for metering purpose. How we can make use of IT to optimize optical or capital costs, reduced operation and maintenance cost. So how is the transition from conventional grid to the smart grid? In smart grid, we need the power generation from centralized along and addition of more and more renewables, electric vehicles likely to come. Power flow becomes bidirectional. There should be two-way communication from the utilities to the customers. Electromechanical meters needs to be replaced by the microprocessor or digital meters. So this smart grid needs to have this property like self-monitoring and self-healing. At the end, whether it is conventional grid or smart grid, what way the customer gets benefited. So it is expected that in smart grid, customer will have choice. So there will be no more monopoly in the same area. There will be more than one utility supplying power. So customer can switch over depending upon their wish. Okay, so these are some general explanation. I will not go into that. So subsystems of smart grid, you see basically three important parts: infrastructure. From infrastructure, we have these power systems, generation, transmission, distribution. Then we have renewable power plants. Talking about the smart information systems in terms of smart meters, sensors, phasor measurement units. Talking about the smart communication subsystems in terms of fiber optic communication and how we will manage these smart systems. What will be the management objectives in terms of we want to manage the we want to reduce the losses, we want to manage the demand profile, we want to reduce the emissions, we want to improve the efficiency. So there can be different objective. How this smart grid will be managed, what kind of optimization tools and techniques we are using. Then how we'll protect this smart grid. Protection is very important aspect. Protection, and then of course maintaining the privacy and security of the data is really very important. So we have almost completed. I have supervised large number of PhD, masters, postdoc students who have significantly contributed in this research publications, contributing several chapters in the books in the areas of like power system protection in the smart grid, distributed generation, renewable technology, hybrid power systems, even in the thermal power plants, how we improve the efficiency, even in this power electronics area, power drives, advanced applications. And these are some of these important reference. Particularly, I was mentioning about this book. I significantly covered from this book. Very nice book, Renewable and Efficient Electric Power Systems by GM Masters, by IEEE Press Wiley. This has version 2004, first, then second edition. So even this 2004 might be easily available. Okay. Then several books, as I showed you, and then several important research papers contributed by my research students in these areas. Okay. So I will just stop down here. Thank you very much for your kind attention. And now I'm happy to have a discussion, interaction. I think now we probably no need the break. We can relax and just happy to discuss and take some questions. I hope you enjoyed this presentation. Of course, the material I covered, it can take whole day.